In this video, we are going to solve problems of finding the last digit of a given number. Okay. So for example, I take a number which is very large. Say, suppose I take a number like 3 to the power of 100. Okay. And now I'm interested in finding the last digit of, now this is a very big number. This is a very huge number. And I'm interested in finding what is the last digit of this huge number. So let us try to see how to solve this kind of problems. So for this, I have to recall Euler's theorem. So let me just quickly recall it. What does Euler's theorem say? That if I have two integers a and m, which are relatively prime, so that the GCD is 1, okay, then I can say that a raised to phi of m is congruent to 1 modulo m. This is done in the previous video. We have discussed about Euler's theorem. Okay, and now let us try to see how to use this theorem to find the last digit of a given large number. So remember, whenever I want to find the last digit, what we have to usually do is you have to choose m equal to 10 in the above theorem. You have to choose just m equal to 10, right? So because if I take a modulo m of any number, I'm going to get the last digit. So we will always choose m equal to 10. So now let me write an exercise. Say, let us find the last digit of say 303 raised to 102. Okay. Now how am I going to find the last digit of 3 raised to 102? Clearly in the Euler's theorem, I have this, you have a, and here you have 3. So 3 and so a is 3 is going to play the role of a in this problem, because it is a raised to something. Here you have 3 raised to something. So clearly, what is the value of a that I'm going to choose? A that I'm going to choose is 3. And what is the value of m that I'm going to choose from the Euler's theorem? The value of m, as I told you, the value of m will be equal to 10. We will take this value of a and m and substitute in the above Euler's theorem statement. So we know that GCD of 3 and 10 is 1. So certainly I can use Euler's theorem. Now we are eligible to use Euler's theorem. So I will write by Euler's theorem. Let me write the statement a raised to phi of m is congruent to 1 modulo m. This means that 3 raised to phi of 10, 3 raised to phi of 10 is congruent to 1 modulo 10. Okay, in the previous lecture, we have calculated what is phi of 10. Okay, still I will just show you here in a rough column. So what is phi of 10? I can write as it as 10. I can factorize as 5 into 2, and if I can write it as phi of 5 into phi of 2. 5 and 2 are prime numbers, so phi of 5 will be equal to 5 minus 1. You can see the previous videos where we have calculated Euler's functions, and this is 2 is also prime number, so this will be 2 minus 1, so it will be 4 into 1, which is 4. So the conclusion is that phi of 10 is actually how much? Phi of 10 is 4. Okay, let's get back to our step. So we are continuing here. So I have 3 raised to 4 is congruent to, because phi of 10 is 4, so 3 raised to 4 is congruent to 1 modulo 10. Okay, now this important statement that we have reached, that 3 raised to 4 is 1, but we want to actually, in the question, we want a power of 102. You see here 3 raised to 102 we want. So we have to connect 102 and the fourth power. So 102, if I divide by say 4, okay, by, because I have a fourth power here and I need a 102th power, right? So I'm dividing 102 by 4 simply. So I'm getting, what was the 8 and this is 22 and 4 5 is the 20 and the remainder is 2. Okay, so this 25 is an important number for me right now. Okay, so I'm going to use this number 25. So I'll say I'll take the powers of, I'll take the 25th powers of both the sides. So if I take 25th powers, what will I get? 3 raised to, I hope it is understood why I'm taking the 25th power, because I got the answer as 25 when I divide 102 by 4. What is 102? 102 is the question, the power in the question. 4 is the power that we have got here. Okay. So 3 raised to 4 raised to 25 is congruent to 1 raised to 25. I've raised both the sides by 25 modulo 10, and 3 raised to 4 is to 25 is 3 raised to 4 into 25, which is 100. It's congruent to 1 modulo 10. Now we are only 2 powers away from the given question. So I will multiply both sides by 3 square. See, I have 2 plus the power, the remainder is 2. Right. So multiply both the sides by 3 square. So I will get 3 raised to 100 into 3 raised to 2 is congruent to 1 into 3 raised to 2 modulo 10. So this will give me 3 raised to 102 is congruent to 3 square modulo 10, and 3 square modulo 10 is 9. This is 9 modulo 10. So we have reached a conclusion that 102, 3 raised to 102 is congruent to 9 modulo 10. This means that if we divide, what is the meaning of this? If we divide 3 raised to 102 by 10, the remainder is equal to 9, which means that the last digit of 3 raised to 102 is also 9. I hope these two statements are clearly understood. See, if I take a number, suppose I take a number 56, and if I divide it by 10, any number if you divide by 10, whatever remainder you get, that remainder is always the last digit. Here 56 has last digit 6. Right? So if you divide any number by 10, you can take any number instead of 56, divide it by 10. Whatever remainder you will get, that remainder will be exactly the last digit. That is why we can now, from above statement, when I write that when 3 raised to 102 is divided by 10, the remainder we got is 9, and this remainder must exactly be the last digit of that number. Therefore, the last digit of 3 raised to 102 turns up to be exactly 9. Okay, let me take one more problem so that it will be more clear to you. So let me take find the last digit of, let's take 7 raised to 44. Okay, so what is the last digit? Again, I'm going to, as the same, I'm going to choose the value of n equal to the value of m in the Euler's theorem. M is 10, and the value of a that I'm going to choose is 7. I know the statement of Euler's theorem is GCD of a and m must be 1. So the GCD of 7 and 10 is 1, And what is the statement? The statement says that Euler's theorem states that a raised to phi of m should be is congruent to 1 modulo m. So let me put the values of a and m in the statement. So 7 raised to phi of 10 is congruent to 1 modulo 10. And what is phi of 10? In the previous problem, we have seen that phi of 10 is 4. You can now remember this. This is the important um, formula, as you can say, that phi of 10 comes to be 4, so that you can be faster in your problem solving. So this is 7 raised to 4 is congruent to 1 modulo 10. And now again, we have the fourth power here. And in the given question, we have 44th power. Let us quickly change, because I really didn't expect that 44 will be solving a problem for 44 will be that easy. So let me just take it to be 46. Okay, this would rather make a sensible problem. So let me raise the, so whatever I'm saying is, now let's divide the number 46 by the 4 number, the number 4, because we have the fourth power. So I know that 4 11s are 44, and I have remainder 2. So this 11 is the power which I should be really taking. So take the 11th power. So 7 raised to 4 raised to 11 is congruent to 1 raised to 11 modulo 4. 1 raised to 11 is 1. So the 7 raised to 4 raised to 11 will become 7 raised to 4 into 11, which is 44, is congruent to 1 modulo 10. I'm 2 powers away now because I want 46th power. So I have 2, the remainder is 2. So let us multiply by 7 square on both the sides, because 2 powers I need. Multiply by 7 square. So 7 raised to 44 into 7 square is congruent to 1 into 7 square modulo 10. So this will give me 7 raised to 46 is congruent to 7 square is 49 modulo 10. Now what is 49 modulo 10? 49 modulo 10 means last digit of 49. Means the last digit of anything. When I take modulo 10, it means the last digit. Last digit of 14. What is the last digit of 49? The last digit of 49 is 9. So 7 raised to 46 is the same as 9. So I'm picking the last digit, 9 modulo 10. So this eventually the statement that we have written here is trying to tell you that if we divide what? If we divide 7 raised to 46 by 10, the remainder is how much? The remainder is 9. If I'm dividing any number by 10, and if I'm getting the remainder 9, it means the last digit is also 9. Therefore, the last digit of 7 raised to 46 is also 9. This is the way we calculate the last digits of given such large numbers using Euler's theorem.